Good evening, everyone. I think we'll get started now. Welcome to everyone in the room and those who are online. I'm Warren Mueller. I'm the Secretary of the Statistical Society of Australia Canberra branch, and each year we have the pleasure with the Canberra Data Science Group and this year with IEEE ACT to organise a joint meeting and hopefully choose a topic which is going to be of broad interest to right across the disciplines that all those groups cover. The Statistical Society meets once a month other than around December, January, and also runs various workshops, gives their members discounts at conferences, funds students, and a lot of other activities as well. So just Google Statistical Society of Australia if you're interested in it. I'm going to ask Yan Chang, who runs the Canberra Data Science Group, to open the proceedings and introduce the speaker. So it's over to you.
Thanks, Warren. Good evening, everyone. My name is Yan Chang. I'm a research scientist with CSIO based in Black Mountain. So I would like to begin today by acknowledging the Ngunnawal people who are the traditional custodians of the land which we gather today, and pay my respect to their elders past and present. So myself here, I'm representing the Canberra Data Scientists meetup and also the IEEE ACT section, where I am a chair of the Computer Society. So Canberra Data Scientists meetup group, we have over 900 members, and we organize the seminars and the network events like bushwalking as well. So if you would like to join us, feel free, to go to the link at the bottom of the page. And I would like to thank, the Statistical Society of Australia and also the IEEE ACT section for co-organizing this event. And also would like to thank Shua and whose director is Zunaid Kamal for sponsoring this event. So Zunaid has been my long-term friend, has been sponsoring our event in the last years. And with SSA Canberra, and we have been organizing joint events every year since 2017, so already 6 years. Thank you, Warren and Francis, for working together with us for organizing the seminars. So, okay, this session will be recorded. Warren, is it will be recorded by Francis, right? Okay, yes, it will be recorded, and please keep your questions at the end of the talk. And for people attending online, you may want to type your questions in the chat function. Okay, next I would like to introduce our speaker, Dr. Stephen Wang, and he will give us a talk on ChatGPT and large language models. Stephen Wang is a principal research scientist at CSIO, and his research in computational linguistics employs methods from fields such as natural language processing, machine learning, information retrieval, and human-computer interaction. He has got over 20 years of research experience, and he led projects resulting in the development of NLP systems in industry and government. Currently, he is a team leader of the language technology team, and his research interests are AI for science, computational social science, and text-driven business analytics. Okay, over to you. Please join me to welcome our speaker, Dr. Stephen Wang.
Thank you for that warm welcome, Yang Chen, and good evening, everyone. Just give me a moment to stop the slides over. So hopefully the slides are now sharing. Just try and get rid of this. Okay, I'm not sure how to get rid of that banner at the top. That's okay. So, good evening, everyone. So my name is Stephen Wan, and it's a pleasure to present to you here this evening. As Yang Cheng said, I lead the language technology team at Data61 CSIRO. And being in the field of natural language processing and information retrieval for over 20 years, it's really quite amazing to see how the field has progressed to this point. Technologies like ChatGPT and large language models do an amazing job of generating text and also seemingly in reproducing knowledge, human knowledge that's reported in that text. So what I'd like to do this evening is share with you my perspective on these technologies as a computational linguistics researcher. And my aim is to help maybe cut through some of the hype around ChatGPT and large language models, but instead look at how these models are representing language, what aspects of language are they representing, so that we can understand how is it that these models do this kind of job. And along the way, we'll have a look at some of the limitations of these technologies and have a look at how we can address some of these issues. So this is the starting point to ChatGPT. We start, if you haven't used it already, you start by entering a question, and in here I've asked it to tell me why ChatGPT itself is groundbreaking, and then tell me what the limitations are. And based on that, ChatGPT will then generate some text based on all the data that it's been trained on. It doesn't retrieve this text like a search engine might. It generates this from scratch. So I'm guessing that many of you will have played with ChatGPT by now, and you are maybe thinking about how you might use tools like this. And at a high level, this is my perspective on these tools. I think it's great for things like drafting text and highlighting key content within some documents or content that we might upload, perhaps. So productivity gains around reading and writing, I think, are a key benefit. But like any tool, it has strengths and weaknesses. And so we'll go into some of these a little bit later on. So we have to use these tools with care. Thank you. So let's have a look at ChatGPT to see why I say these things. So we can make some observations. And the first is we can see how good the prose is. It looks convincing. It's so convincing that people will read the generated text and believe it without questioning it. The second is that it looks like it's doing an amazing job at creating an answer to my rather complex question. On the surface of it, it looks like I've saved quite a bit of time. I don't need to go to the web and find the relevant documents and read through them to then assemble my own answer. Or do I? Really, perhaps as good as this text looks, maybe I should be asking things like, what information is it omitting? What kinds of content is missing? So another observation I can make is so here in the generated text, it has included the information about this thing called a transformer architecture. And this is indeed a key concept in this field. And so perhaps if I'm learning about a new topic, I can use tools like this to at least set up a list of things that I need to go away and research further, even if I don't completely trust everything I read in the text. So there is a technology disruption here. And to me, the disruption is this, that OpenAI released this model via an API, and it opened the door to the development community to create all sorts of applications. Here's an example of an application here. You can see it looks like a PDF on the left-hand side, and on the right-hand side is a chat window. And this one's called Chat PDF. So here I've uploaded a scientific article, and I've asked it to tell me what the key contributions are, highlight those, and then show me what content relates to the chat comments that it's making on the side. It's not perfect, and you will encounter some issues if you go to this site to use this tool. But the point here is that almost anyone these days can build a tool like this. As long as you have basic software engineering capability, you can start to put together tools like this using APIs. Here's another example where researchers wanted to create a chat system for the public so that the public could ask questions about climate change. And it would respond using information that came from the most recent report from the Intergovernmental Panel on Climate Change. And the point here is to communicate the scientific findings to the public, noting that there's a lot of misinformation out there about climate change. And so they wanted to provide a resource for ordinary people to use. Again, I'm showing this example to show how easy it is to put together tools like this using the APIs. It's important to note that some of our data is sensitive and maybe we can't upload it or we shouldn't upload it to the cloud, and we need to be careful of how we use cloud resources with sensitive data. And so there are a number of software packages that have come, that have arisen recently to address this issue. And this one here is called H2O GPT. And this one provides a code base to try and help run those language models locally and to keep your data local. I should note that they call these large language models for a reason. They are incredibly large, and the engineering challenge to get those language models running on local computing resources is not trivial, but we can start to think about how we build applications that might be careful of our sensitive data. So those are some of the tools, ChatGPT, large language models that I want to look at today. And I want to, in the next part of this talk, look at the technology underpinning this. So the technology from the family of neural network methods called the transformer model, and look at some of the methods that have come up since the transformer model was introduced that led to ChatGPT. And I'm deliberately keeping this part of the talk at a very high level so that we can link this back to earlier research in language technology and linguistics. Again, to see why is it that these models are able to do the things that they do. So let me introduce some technology. First is large language models. These are the language models that are representing language trained on large collections of data online, for example, Wikipedia, and they were trained on book collections, and more recently, they're trained on curated representation, curated archives of the web. So large language models, or LLMs if I abbreviate it, are what we're talking about. In some circles, they're also known as pre-trained language models, particularly in the computational linguistics, natural language processing fields. In fact, GPT stands for a generative pre-trained transformer. So we've got a nice timeline here of all these different models. And it starts with the introduction of the BERT model in 2018. And when I made this image, the online documentation didn't quite have ChatGPT on it yet, so I put that in there myself at the end of 2022. Since 2019, the models have become larger and larger, and the community tends to refer to models from GPT-2 onwards as the large language models, given how many billions of parameters, we're talking hundreds of billions of parameters in these models. And so you can see here there are a range of models, and they are all subtly different, and we can use them for different things. So for example, some models are great for doing things like text or token classification. Some are useful for text summarization. Others are useful for things like image caption generation. And so when the BERT model was introduced in 2018, it was also a massive disruption, and it triggered a lot of excitement in the academic community, and there were a lot of workshops and conferences on the theme of BERTology. And this is the study of the BERT model, so that we could try and figure out what kind of linguistic phenomena is being captured in these models. So as I said, as a community, we were amazed by what the model could do and why. And so it's interesting to see how this level of inquiry is again happening with today's large language models. So we should note too that BERT was also built on a foundation of earlier work in the era of statistical natural language processing. So during this time, we were introduced to statistical machine translation, text summarization, and of course the advances in web search technology that we take for granted these days. What I find particularly interesting is that many of the technology questions that we're examining today with respect to ChatGPT and large language models, these have an analog in the era of statistical NLP. So for example, in 2005, Philip Cohen and colleagues took the repository of European parliamentary transcripts as a huge database of training examples for machine translation. And this really catapulted statistical machine translation technology into the spotlight. Some years later, in 2009, Google released its collection of word sequence statistics or n-gram statistics. And these were based on the digital book collection that it had in the day. So I find these interesting and I'm focusing on these two because we can think of these two blue blocks as an abstraction of the key functions in generating text. So we can think of translation, or if you want to think of a related problem of paraphrase generation, we can think of this as a case where we need to substitute a word or a phrase for another of similar meaning. And there are multiple possible substitutions. So we can use a language model to decide which of these substitutions are the most appropriate given the context of the overall generated sentence. These days, instead of having a statistical model for each block, today we have a single neural network model that captures both of these parts in an end-to-end system. But even with our more elegant neural network approach, I'm still quite fond of this particular abstraction of text generation. So loosely speaking, we have to model the choice of what to say, and that's content selection. And we also have to model the choice of how best to say it. So what are the words and word ordering that we can use there. So those statistical language models are able to rank sequences of words, and in applications, we see these used in things like text autocomplete. So this is an example here from Google, which needs little explanation, I imagine. So based on the context of what has been written already, the model can assign a probability to certain words that can follow, and the system will decide, based on the probabilities, how to rank these suggestions for the autocomplete, or if it's translation, how to rank those translation candidates. So the more recent technology, the transformer models, they differ from the statistical language model in that they move away from statistics about the word occurrences to something a little bit more abstract. The transformer models start by mapping those words to a vector of numbers that represents meaning. And we call this type of approach distributional semantics in the field of computational linguistics. And that as a field includes methods like latent semantic indexing, topic modeling, for example, with latent Dirichlet allocation, and other work on embeddings that predates the transformer model. Basically, there's a representation, a vector representation that is learned, where for words that are similar, the vectors are in a similar space. So we look at this example here. If there are words that are closely related names, they will be mapped to the same space, or same with words that are synonyms or closely related concepts, or slight variations in the word form. So the difference between singular and plural form for a noun, for example, and these will be mapped to vectors in a similar space. The embeddings are such a good approximation as a representation of meaning that we can even attempt things like analogical reasoning with them. And so here's an example with the reasoning around analogy. So we can take the vector for the concept of king, we can subtract the vector that represents the concept of man, and we can add the vector that represents the concept of woman. And then we can see the resulting vector, which word is closest to it in the vocabulary. And in this example, the word that's closest to it is the one that corresponds to the concept of queen. So it was astonishing to the research field at the time that with these basic representations of meaning as vectors, you could map analogical reasoning to vector mathematics. So actually, we can trace this contextual notion of meaning to earlier work in statistics, to the work of Wittgenstein and Firth. And these two are typically cited in computational linguistics work on distributional semantics. And I particularly like the quote attributed to Firth. I think it's quite poetic. You shall know a word by the company it keeps. So all that to say is these recent models can trace their lineage back to earlier work in linguistics. So what does this all look like when we come back to the transformer? Contextualized representations of meaning are at the heart of the transformer neural network. So in the paper by Vaswani and colleagues, which introduced the transformer architecture, they called that paper "Attention is All You Need," where attention refers to the mechanism that picks out the contextual features that are relevant to each word in the input text. So here's a high-level representation of that neural network of the Vaswani transformer architecture, and it takes as input, in this case, an example from a French sentence, and the output is a translation in English. So inside the transformer architecture, there you can see that there are repeated neural network structures. There are two stacks there. One's called the encoder stack, the other's called the decoder stack. And unsurprisingly, the encoder is responsible for representing the input, and that representation is then sent to the decoder stack, which then generates the output one word at a time. So let me zoom in into one of these repeated blocks, and we can see that to begin with, the words are mapped to that embedding in the first layer or that bottom layer. Then that embedding representation, so that's that x1 and x2 green vector there, that's sent to the attention mechanism, which adds that contextual aspect to that to the basic embedding representation. Then there's a feed-forward network which generates a resulting vector that represents the meaning of those words that are now contextualized, and these are then sent to the next layer in the neural network stack. The decoder block is actually quite similar, so I'm not going to zoom into that. The main difference is that it takes the final state from the encoder stack and uses that as the input to start generating the words one at a time for in each position. So the part that I'd like to focus on today is the attention mechanism, because I'm interested in how that's able to capture key information from the text. So the attention mechanism, here's a visualization of what that mechanism is modeling. And you can see on the left-hand side, it's learning to weight the importance of each pair of words within that input text. So on the left, you can see a lot of these pairings visualized. And on the right, if we look at the associations that matter most at a particular point in the sequence, so in this case, it's the pronoun it's, we can see which associations are most important for sort of explaining the occurrence of that word it's at that point. And you can see that this is important information when it comes to resolving that pronoun. So which concept does it refer to? It refers to the phrase the law, and the attention mechanism is able to learn the importance of that feature in predicting the occurrence of that word at that position. So what I think is an interesting question is this: how do language models capture some of the aspects of knowledge that we observe when we read the generated text and things like ChatGPT? How is it that it's able to do so well at making this plausible looking text? So here I've represented a sentence, and the colored blocks represent the embeddings. And on the top there, you can see a subset of the contextual pairings of words that might arise from the attention mechanism. And the point is that these associations that are learnt through the attention mechanism, they can often correspond to key semantic information that we care about. So For example, you can use those links to answer questions like, what is the model name? The model name is GPT. And by keeping track of pairwise associations in that context, we can learn that. What kind of model is it? It's a language model. And again, this is something that could be represented in this pairwise relationship between words. So what kind of information can we capture this way? Minimally, I think we can think of these as answers to simple questions. So WH questions, for example, the ones beginning with what, when, why, where. And in prior work, looking at Wall Street Journal dataset, researchers found that 70% of semantic relationships occur in adjacent word positions. And this goes up to 95% when we consider word context of size 5 words, which is why I think earlier statistical methods did so well. Methods like hidden Markov models did so well in modeling language, particularly when it comes to answering questions. So knowing this, it's not surprising that the language model can capture things like common sense knowledge. For example, fire is bad because we know it's damaging, and damaging has a negative sentiment. We can capture things like facts and figures, particularly around geography. So in Wikipedia, for example, we often see that the city name is followed by the country that it is situated in. And we can see how this can apply to commonly reported scientific knowledge. And interestingly, it will also capture cultural norms and biases. So you can see in the last example there, by looking at that local word context, you'll end up capturing things like gender, the biases and prejudices around gender and professions. And so the attention mechanism, by capturing these word associations, can at least be capturing these kinds of knowledge. The transformer language model that we just saw, we see that in the applications like ChatGPT, they're applicable to a wide range of domains. And that's quite an amazing advance, really. And one of the reasons for this is multitask learning. So here's an older model called the T5 model from Google, where they began to look at trying to do this multitask learning, where the transformer model is trained not just to do translation, but to do 4 things at once. So in this case, it's learning to translate. It's learning about being able to score sentence acceptability. It's learning something about paraphrase generation and semantic relatedness. And it's also learning to summarize. So all that the training data set covers these 4 things. And the key intuition in this is, with multitask learning, the model learns something in one task, which will be helpful in the other. So for example, a model that perhaps knows how to judge the semantic relatedness of 2 texts might do quite well, perhaps in generating summaries. So with multitask learning as part of the transformer model, as being used to create the more recent transformer models, we can then take the resulting model to generate a response to instructions like this. So we call these instructions on the left-hand side, we call these the prompts. And once we have these prompts, we can put that into the transformer model, and the resulting text that's generated will be conditioned on those prompts. So you have the encoding of that prompt, and then it starts to generate the very next word that would come after that. And that generated text will be the response to that instruction. So that's the technology at a high level behind something like GPT. And so how do we get to ChatGPT then? Well, ChatGPT itself is a black box. We don't know, us mere mortals, we don't know exactly what's happening under the hood, but we do know that it's based on an earlier system called InstructGPT, for which there are some publications. So what's special, I think, about InstructGPT is the way that the research team went about sourcing additional ground truth data sets to train the model. So these are data sets like the slide before, collections of prompts and the resulting outputs. And on the left here, you can see some examples of the types of prompts, the categories of prompts that they wanted to collect, and some examples of the prompts themselves on the right-hand side. So they were that research team looked at generating and curating a data set that was explicitly targeting some interesting cases. For example, looking at prompts to do with open-ended essay-style questions, which are normally quite challenging, and also things like brainstorming dialogues. So this is why when you use ChatGPT, it's able to do these kinds of tasks. And what's more, when they were preparing those data sets, that research team took extra care to prepare those data sets using the principles of trying to be helpful, trying to be honest, make sure the data resulting data was truthful, and they wanted the curated data set to represent text that was not abusive. So they wanted to avoid harm. So they wanted to be helpful, honest, and avoid harm. Because these are the ideal responses that they wanted the AI to emulate. So ChatGPT is a refinement of things like refinement of GPT, refinement of these transformer language models, where it's based on these extra data sets, these carefully curated data sets around instruction and chat-oriented data. So moving along, let's have a look now at some of the pitfalls and challenges with these models. So the first issue that probably pops into many people's heads is so-called hallucination. So some of you may have seen this recent news article. Two lawyers used ChatGPT to prepare some legal briefs, and they went to court with those legal briefs, but they didn't check that the generated content was accurate. And in fact, ChatGPT made up some plausible looking text that looked like relevant cases for legal research, but this was of course all made up. So this example here, this case is fast becoming a warning sign of what not to do with ChatGPT, which brings me back to that advice at the beginning of the talk. We need to be careful about how we use these tools, and we need to be responsible for the way we use them. In fact, if we go back to that climate chat application, the intention there was to combat misinformation about climate change in society. But large language models also have the potential to generate misleading text. And you can see the warning sign at the bottom to this effect. So large language models have been described by others in the computational linguistics field as being plausibility models. Actually, they're not knowledge databases that we can use like we do with any other database. So how can we tackle this problem of hallucination? Well, it's an active area of research in the field, and it's an unsolved research question, as you can imagine, but I'll mention some of the directions that we're having a look at. So the inaccuracies in the generated text arise because we're doing probabilistic text generation, albeit with a very sophisticated model. And so coming back to that abstraction of the text generation process that I mentioned earlier, I wonder if there's more to be done in neural network generation and the constraints that we have in the decoding algorithms, so that these are better able to handle that first part of content selection. So can we choose the content that is going to lead to a generated text that doesn't suffer from these hallucinations or this inaccurate text? So in the statistical natural language processing era, many in the field were looking at how do we utilize semantic and syntactic structure in that decoding step of the text generation process. And here's some work on the left-hand side that we were involved in as well, where we incorporated semantic structures into the text generation process. So as we generate the text, we see what kinds of semantic structures we're constructing, where we have provided some input of the kinds of semantic structures that we would like our text to have. And we check as we go along that our generated text indeed is matching those semantic structures. So we're taking these ideas, our team's taking these kinds of ideas and borrowing from these approaches and seeing how we can inject external representations of knowledge into the neural network mechanism. So for example, in the attention mechanism, it's able to capture knowledge and a representation of what's important at a particular point in the generation step. Can we inject extra information into the attention representation in that decoding step so that we can help influence what text is being generated, and so that again, that it minimizes the risk of hallucinations, or does better at a range of related inference. So there are actually many reasons why we want to inject information into the large language models. For one, the large language models, they only represent the information from a static repository of text at a particular point in time. So if we're using it for inference, and we're doing that inference today, we may need to add more recent knowledge into that inference mechanism. Or we may have taxonomies that we want to include within that inference mechanism, and so we need to inject that into the inference step. Perhaps we're designing a new taxonomy, or we're using a taxonomy that is bespoke to where we work, for example. Or we might want to incorporate user knowledge into that inference step. So the user's context is crucially important. It helps guide the AI in deciding what is relevant at a particular point in time. And so maybe we want to inject information about the user's context and their representations of knowledge that is important to bring to bear in this kind of situation, include those into the neural network. So that was hallucinations. I'll mention briefly one other issue, and that is the reliance of these language models on very large data sets. So we know that our social prejudices are reflected in language data. So here's an example from 2016, a well-known example where Microsoft released a chatbot, and the aim here was that chatbot would learn from the interactions on Twitter, and it would update its language model based on those interactions. Unfortunately, very quickly after its release, that adaptive chatbot soon learned to produce racist text, and so that chatbot was taken down within 24 hours. So this is again another one of those warning signs. And fortunately, researchers on that precursor to ChatGPT, the InstructGPT system, they took those steps to curate that training data so that they could avoid emulating harmful or hateful text. But it's important for the research community to think about how AI, algorithmic and data bias affects the behavior of the system. And it's a reminder for us to think about the social consequences of including these kinds of inference mechanisms into the applications that we build. And indeed, the community is looking at this. So here's an example of a recent paper by some of the thought leaders in the field. And they're again advocating the need to consider responsible usage of these large language models. So to wrap up, I'll give a brief overview of the kinds of research that we're doing at CSIRO Data 61 with large language models in the area of AI for science. So a scenario that I quite often hear is this: can we use the large language models to extract information from text for our own scientific research? So here's an example of a scientific article on the screen here. And the point of this is that we want to tap into scientific literature, which is a treasure trove of reported scientific knowledge and data. And if only we could extract that data out and use it in our downstream simulations or downstream data modeling. So we're looking at how we use large language models to do this, to first find the relevant documents in that sea of an exponentially growing set of scientific literature, find those relevant documents, and then once we found them, can we use the large language models to extract out those numeric values from the text? So I'll stay at the application level, but we've been looking at this in the context of a collaboration with CSIRO Agriculture and Food and their work on crop simulation. So it turns out that for their crop simulation tool, to set up new simulations takes an enormous amount of work. So for each new simulation, there are thousands of parameters to initialize. And researchers typically have to trawl through scientific literature for each of those parameters to find plausible values to initialize that simulation. So for example, if we wanted to vary, if we were looking at planting crops and we wanted to vary the spacing between the rows of those with rows of seeds that we might plant, and we were interested in doing this, say, for some crop like wheat, the researcher has to find the plausible values to use in the simulation, and they will go through scientific literature to see what values have been experimented with in prior work. So the system helps by doing the following. For each simulation parameter, it conducts a literature search to find the relevant documents. And for the relevant documents, it pulls out the reported values and then puts all of those reported values together to create histograms, distributions like the ones you see here on the screen. So there are three particular parameters here: water use efficiency, radiation use efficiency, and leaf area index is the one on the bottom. So instead of spending months searching through scientific literature for that information, we can straight away present these distributions directly to the researcher and say, well, here are the reported values that we found, that the system has found on the web, and then the researcher can say, okay, well, we can use that information to initialize the simulations. It's important to know that it's important to design such a tool so that we allow the user, a scientist in this case, to vet those results. So the information is extracted in our natural language processing pipeline in such a way so that it preserves links back to the source information. So the distributions are clickable so that when you click on that, it directs the researcher back to the supporting information. So you can see the example text that pops up if the user clicks on one of those points, which are hyperlinks, which allows them then to track back to the original source PDF. So they can use that information to say, all right, this looks like a plausible value. Can I verify that it is? Click on the links and they can make that decision and then use that in the simulation. So to conclude, it's an exciting new era in natural language processing and language technology. It's very easy for data scientists now to try these methods out, particularly with the prompt-based approaches through the APIs. And we can consider these as some of the new baselines in natural language processing systems. As I said, the barriers to entry to use these kinds of technology are lowered dramatically. So I've seen startups with very basic engineering skills put together quite compelling dialogue systems with their own data. And it's really been quite amazing to see that this is no longer limited to natural language processing teams. So many people can jump into this. So we saw how the attention mechanism can lead to these contextualized embeddings of representations of meaning, which allows us the possibility to capture some elements of knowledge. So we can see how is it that these systems are able to capture key bits of information and key knowledge from text. We saw that it's not perfect, and there are going to be some scenarios where we want to inject knowledge into the large language models for inference for some of the other applications that we're interested in. So we can, in this case, be guided by prior work in computational linguistics and statistical natural language processing, and pull in expertise from other fields like human factors to consider that user perspective. And indeed, other disciplines like social science, economics to guide our understanding of how we conduct further research in this field of large language models. Thank you.
Okay, so thanks, Stephen, for your excellent talk and the introduction of the ChatGPT and big language models. And before we go into the questions, and we have our food delivered, just need a few volunteers to help us bring the food upstairs. Can someone, we do maybe for a few people? Thank you very much. Okay, now is a question time. Do we have any questions from the room here, please? Any questions? Raise your hand.
Do you think we would be soon able to exactly find out if a text is written by ChatGPT?
That's a really good question, and there are approaches to try and detect that, but it is hard. So there are approaches, for example, to try and apply things like watermarking methods to generate a text, but it is an open research question at the moment. In fact, the Australasian Language Technology Association, the sort of research association for this field, which I'm part of, has made for its shared task for this year, I believe, that exact problem of trying to develop systems to detect with this generated text. So there are some methods, but I think they're not completely foolproof at the moment. So it is a very hard question and a very difficult one to solve. Yeah.
So determining at the moment is planning, they can detect the text written by ChatGPT maybe not.
Yeah, I've seen some of those claims, and I'm not, or I've seen some of the related work that shows you can in some contexts detect whether the text is generated by the large language models, but I think it's a case that I think there is still many challenges, still quite a few challenges in that area.
Okay, because we have audience attending online, and they won't be able to hear you guys. We only have a wired mic here. I just wondering, if you have a question, would you mind come over here to ask your question so that people online can hear you guys? Thank you.
I just wanted to follow up on the question asked whether we can detect the text generated by the language model itself. You discussed some potential harms of using these large language models during your presentation. And I just wanted to know your views on the impact of tools like ChatGPT on education. Like, for example, universities having all their assignments, especially, programming assignments and essay assignments, and like students using these as a way to cheat and do those assignments. So how do you think like universities or institutes should tackle this going forward, since we don't have a way of detecting things done by ChatGPT as of now? So do you think this will act as a tool of education on the future, or is it like more harm than use?
Yeah, that's also a very good question. I guess in the research group that I'm a part of, there are those that are interested in the ramifications of these large language models in things like education and also in the workplace. And I think what I've learned from discussions with them is that we need to research this further. There aren't any easy questions here, and perhaps we need to think about how we change the way we do assessments, I suppose, in educational contexts.
Hey, I'm thinking if we're deploying these in terms of production systems that are going out live, how do we establish a quality metric for truth or validity of answers of these things, noting that we can't be reviewing them by a human every time?
Yeah, another excellent question. it's an active area of research at the moment to look at how do we change and develop new evaluation metrics to specifically target this. So for example, in some work that we published last year, we looked at borrowing from image caption evaluation, where they use a metric called the SPICE metric, and they're explicitly looking at the kinds of semantic structures in the generated text and seeing whether or not these correspond to the reference text for those captions. So comparing them back to some source reference material. But I think it was recognized in a shared task on summarization this year that more work needs to be done on this. So even some of our most advanced metrics, which are also based on large language models, they're unable to capture to directly measure the degree to which things are accurate or not. And that's why in the applications that we're building, I think it's important to consider the user perspective in this. I mean, a user needs to be able to use these tools knowing that they are going to be imperfect, and they are AI and machine learning systems are going to make mistakes from time to time. So I think the way we engineer those solutions is such that we allow the users the capability to validate, to do those reality checks for themselves. And so being able to show the source material, for example, to track back, to look at why the large language model generated a particular thing, or the AI system generated a particular thing, showing the source material to help explain that, or the source text material is what we need to focus on. And so that's why I think we need to have a multidisciplinary approach where we combine not just machine learning and computational linguistics, but also look at fields like human factors. Yeah.
Thanks so much for an excellent talk, Stephen. It was great. I really appreciate how intuitively you explained it, and I feel like really gained a deeper sense beyond what I've been able to absorb from kind of what I've read on Twitter and stuff in the last 6 months. One of the kind of hype trains that I was aware of on Twitter, and I guess the hype pendulum kind of seems to swing back and forth, that some people say, wow, this is amazing, and then other people say, no, that's crap, was around how there's kind of unexpected gains in performance of an LLM that come just with scale. So like I've seen a couple of papers commenting on how just by adding scale, all of a sudden certain LLM systems start to be able to achieve certain tasks that are kind of were thought to be out of scope from what they were explicitly trained to be able to do, sort of thing. And then I've kind of also seen commentary in the other direction saying, oh, well, that might be to do with the fact that those training tasks were actually in the training set for that model, or that they're kind of over exaggerating. But are you able to comment on that, how kind of the fact that LLMs for a while didn't necessarily seem like they were going to be like the model that was going to kind of take the field that next step further, but then this scaling factor seems to have really made sort of a qualitative categorical leap in the kind of apparent performance of those systems?
Yeah, I think as with other areas of data science, something that we've learned even in the statistical natural language processing era is more data helps. You summarize the two sides of that pendulum swinging quite nicely. So yeah, I've read some commentary, I guess, which is asking us to say, okay, let's take a step back from the hype and see, well, were there really examples for that held out scenario already in the training set? And I guess it's good for us to think about how do we rigorously then test this hypothesis that, more data helps. But generally speaking, I think, yeah, the performance of the large language models, I think it does, I think amount of training data definitely is a contributing factor. I think that's bound to help. whether or not it means we can do tasks that are completely unrelated. I think this is something that we need to test empirically through research. So for example, with the multitask scenario that I showed there, so in the T5 model, that was just 4 tasks. Recently, there's an approach that takes this up to 2,000 tasks. And this, I think, contributes to why these large language models are so easy for us to take from one domain to the next. So this makes it really easy, for example, if you're in the startup business, for you to think, okay, how can I use these large language models in my particular domain? So the scale of the data, I think, helps with that generality, and also the multitask learning, I think, also helps with that sort of general model. But even with the multitask learning, as I showed or mentioned in that slide, I think there's a relatedness also between the tasks, right? So when you're modeling things like semantic relationship between sentences, say you're modeling paraphrase, it's likely that this is going to help, even if you didn't train explicitly on summarization, it's likely that that would help with a summarization task. So the tasks themselves are probably not completely independent either.
Yeah, I would give the people attending online a chance. So any questions from people attending online? Let's see where I can see the chat function. Maybe we get to get this. Do we have any questions from people attending online? If yes, you may raise your hand, or because I may not be able to see you, you can simply unmute yourself and ask your question. Okay, I didn't see anything in the chat function, and nobody's hand. Okay. Well, I'll give the chance back to the room here. So, have any questions in the room?
So the question is in relation to the in regards to the training of the models. I noticed that most of the training has been on the English language. Now, is it possible to have like data sets where like other languages other than English? Because I noticed that most of the when you look at the ChatGPT and all the other stuff, most of it has been trained on the English language, so there's a bit of a bias towards the English language. So has there been cases where there have been other languages like French or Spanish or some other language been used to create a something similar to ChatGPT but for a different language?
Yeah, that's a very good question. And I think in the field, there's a bias towards experimenting and researching with English data. In some of the transformer models, they are looking at cross-lingual language models and looking at language models in other languages. So in some of the other transformer models, for example, that they are looking at other languages, but it's true to say that, yeah, I think as a field, we do have a tendency to focus on English, but I think they're starting to look at how they, you can look at other languages in a similar way. I think what's interesting is different languages will also pose different challenges. So one of the things that we looked at here was it was quite easy to separate words out with, say, white space. But in other languages, this is not as easy, for example. So in languages like Chinese, Korean, and Japanese, you don't separate words with white space. So you have some other language problems that you need to take into account at the beginning. But yeah, I think the field is slowly looking at other languages. But as you say, there is a bias to starting with English.
Large language models are basic. That's what's easier. They have lots of fun, right?
Right. So the decoding model and how we generate text, this is seen as a conditional language model. So you, yeah, you're generating the text based on context. Yeah.
Okay,
Thank you. It's been my long suspicion that the pursuit of creativity must be accompanied by some level of imperfection. In the academia, is there a theoretical sort of suspected limit to expecting like quality, like accurate answers from these generative language models? Is there like a theorized sort of limit to be able to generate accurate answers? Because accuracy, like if you're trying to make a model that is generative, does there have to be some level of imperfection that we must expect? I don't know about limits, but one of the reasons why we want to use these language models is I guess you were talking about creativity. We want to generate novel texts, right? And things that we perhaps want to have the capability in the language model to generate things that are different and don't reflect things that it's been trained on, because we want to generate novel fiction, for example, or to help a creative writer to generate fiction. So we want to have that ability, the language models, to generate these to generate content of all kinds. And so yes, if that's what you meant, I think there is a sort of a tug between these two uses for the language model to generate things that either reflect what was seen in the source material, or to generate to capitalize on its ability to generate these new texts for creative purposes. Yes, creative art is part of it, but also I think there are certain things where not there is no one definitive answer. If you think about like mathematical operations, there's only one answer. But if you think about, say, even a very definitive task like machine translation from one language to another, as sort of like a bilingual person, I know that there are cases where, depending on what you're trying to do, a perfect translation of the meaning is not always the best answer. Sometimes you need to sort of use local sort of idiomatic sort of changes so that the local people might understand, even though it's not a direct translation. So do you have to sort of accept some level of imperfection when you're doing certain tasks, just because it is a generative sort of art that humans take? So I thought there might be some kind of like limit as to what you can say is a perfect answer for any given situation. So I thought there might be some kind of theorized limit within the computational context. Yeah, it's a good question. And I think in machine translation, they consider those cases as well. So it may not be the case that you, so for example, if you're translating one sentence into another language, it may be the case that you need to break up that sentence and translate it as two sentences and split up the information that way, because it's leads to a more fluent translated text. In paraphrase, in the study of text paraphrase, which is something that I'm more familiar with, there is this thing called a near paraphrase. So it is very difficult to find examples of sentences that are exact paraphrases of one another. There's always some kind of information loss or difference in information rather between two paraphrases. So how you map from one paraphrase sentence to another, I think you need to take into account, you may not be, as you said, it may not be possible to completely capture all the information in an input text and have it perfectly represented in an equivalent paraphrase, for example.
Okay, thanks for the wonderful questions and discussions, and also thanks Stephen for his excellent talk. And for the concern of time, I think I would like to conclude this session, and because our food is already there. And thanks to everyone who attending us online, and thank you for being with us for the whole of the talk, and the rest of the guys in the room will enjoy our pizza and drink and have our networking time.